Okay, now we are entering something very interesting. So in this lesson we will look at something as simple as thickness, and you will really wonder why I am talking about thickness here and what is so big deal about thickness. We know what thickness is, why are we coming to IIT to learn about thickness? Okay, so you may wonder like that, but trust me, it took a PhD working for 3 years to even define what thickness is, because no textbook tells you what thickness is. So we will define what thickness is, we will learn how to compute wall thickness, and then from there we will go into things like junctions, and because junctions are nothing but building blocks or segregation of different thicknesses, and what kind of problems that can come because junctions, we have the first cut glimpse of that. Okay. Now first of all, why thickness is important, that should be no doubt about it. If you have thick sections, you get hot spots in castings where you get shrinkage defects. If you have thin sections, you can get cold shuts, which is another kind of problem in castings. And the third problem is where you have sudden change from thick section to thin section, there also you get a problem which is cracks, right. So you need to know all the 3 things, thick and thin and thickness gradient or thickness change. Okay. Now conventionally we say thickness is nothing but, in a way, distance between 2 parallel walls. Okay. So if you have a casting like that and the rim of that or flange of that, you can look at, if the 2 sides are parallel, you can say distance between them is thickness, and there is no discussion, that's absolutely right. Okay. But it is valid only when the walls are parallel. If the walls are not parallel, like in some of the places in this particular example, what do? My old definition saying distance between the 2 walls, and of course when I say distance between 2 walls, I mean distance along the perpendicular of the face. I am not taking inclined distance, I am taking the shortest distance. Here what happens? If I have 2 surfaces like that, if I start from bottom surface and go perpendicular to that and go all the way to the top and look at the intersection distance, I get one value, which is, let us say, TP, starting from point P. If I at P2 I draw one more perpendicular and go other side, I get different value of thickness. So moment you have non-parallel walls, this definition is no good because it can give me different values depending on the starting point. Okay, so it's useless for me. I cannot use it for any computation. So what we have done is, in a very simple nutshell, what looks very simple to you here, but took 2 years of thinking. We say definition of thickness, and this can be defined at any point inside as well as outside a part, okay, as 2 times the minimum distance to surface along the normal ray. The normal ray is the perpendicular to the part surface, the blue line or blue arrow. Along the line at a point P, okay, if you walk the distance, the shortest distance to surface is your value, some value, multiplied by 2 is your thickness. You will understand in a minute why multiplied 2 is there. It's there like that. And if you look at other direction, let us say you are walking from P to other side, the green distance is more than the red distance. So between the 2 I take only the minimum value. What I am saying, 2 into minimum distance along the normal 2 direction. So there are 2 normals, 2 distances, between them the smaller one is the red one, which is T1. If you draw a circle there, you find that it is you can redefine thickness as is nothing but the diameter of the largest circle that I can draw starting from that point, which is not going outside the part, which is lying inside the part only. You got this? Diameter of the largest circle that is centered at that particular point where you want the thickness value and lying within the part. Okay. With this definition, yes, that is why 2 is there. Now with that definition, for the same part, if you compute the values of thickness, the picture will look like this. Okay. So you see now, the values can be actually measured at different places. So you can see somewhere the thickest section is 70 millimeters, somewhere thin section is I think 43 millimeters, 46, 11 millimeters somewhere, the blue line. So red is thick, blue is thin. These are not temperature, these are thickness values colored so that you can visualize it nicely. So it's possible to visualize thicknesses now in a complicated casting like this without doing hand calculation of all the circles. You can write a program for doing that. Clear? This part is okay. Now For metal casting we need one more thickness definition, which is we say is radiographic thickness. What is this? We can say that if I just shoot a ray and the distance of the ray is proportional to the color of the radiographic X-ray color, and if I have a hole in the part, for example, I only measure the length of the ray which is lying within the part, which is, if you see intersections, from odd intersections to even intersections. So intersection 1 to 2 you count, 2 to 3 you leave it, 3 to 4 again you count. So if you add up all those odd to even intersections, you get the total metal distance or metal thickness, and you can color the X-ray like picture depending on this thickness. So again, for this part if I take, I can produce these pictures by a computer program. Okay. And if I have a complex casting like that, these pictures are very valuable because I can now use them as reference, quality reference, and I can compare my real X-ray with this picture and say, hey, my real X-ray contains some additional circles which look like holes, you will miss out as holes, but they actually blow holes. For a simple part it is not very important or difficult, but for a complicated part having a reference X-ray is a very valuable asset, and these can be generated by computer programs using the previous equation which I told you. Okay, now we use these walls to create junctions, okay, and most junctions look like English alphabets. Okay, so you have, if you have two walls, it is a L junction, but L can also become a V junction if the angle is less. If you have three walls, it is a T junction, but if you change the angle it becomes a Y junction. Then can you imagine? 4 walls, you have plus, but angle is different, it becomes a X, and if 6 walls, it's a star junction, except here a star is the worst thing that you can have, because as you go from less to more junctions, it only creates more and more heat concentration, solidification problem, hot spot, and thereby shrinkage porosity. So you do not want to have star junction, you want to actually go away from the star junction. Okay. Now we can look at junctions little more carefully. Depending on the internal angle, I can have different junctions, we already saw that. You can change the wall thickness, they need not be uniform. Third, you can have certain fillet radius internally and externally, and you can see variations of L and T and plus junction here. That is still very easy for you to visualize. Now I will make it more complicated, so pay attention. Now look at it, these are also, the first column is still L junction, but do you recognize that L junction? One is a bar L, second is a 3D L corner kind of a thing, and third one is a L in a rotational cross section. The trick is to be able to see a drawing and recognize these junctions, because each junction has its own language, its own characteristics, its own problems. Okay. Similarly T, the middle one is actually a combination of L and T. Some cross sections it looks like a T, some cross section it looks like an L, right? And then the last one is also a plus junction, if you can recognize that, last corner, right corner. Okay. So by and large we will look at junction parameters, we look at the angle, the thickness, and all those things, and later on we will see how these parameters actually affect our shrinkage and solidification. There is a whole section later on talk about how do you control those junction parameters to remove some problems. So let us look at this example and see whether you can recognize on the screen. Look at the screen and see whether you can recognize junctions in this cross section. Okay. Can you see any L junctions? You have to see how many you got it right. Okay. I am only showing a few here, I am not showing all the L junctions here, but you see whether you can recognize all the L junctions in this example. What about T or V? V is anything which is not right angle is V. It could be open V or it is a tight V. Okay. Then you can see some T junctions there. Anyone can see a Y junction anywhere? Okay. Recognize that as a Y junction. And then there is also a X junction. It is not clear here, but that cross section, if you go a little bit up, there is a hole inside, it becomes a X junction there. Okay. So what you have seen quickly in this is wall thickness is a starting point of language of foundry engineers, and we have to worry about, and because castings do have wall thickness variations, we must be sensitive towards thin walls, thick walls, and rapidly changing walls. And how we define wall thickness? The diameter of the largest sphere. Very easy way to calculate or imagine the thickness. Anywhere you have problem, you can use this as a starting point. And radiographic thickness for simulating X-rays. Plus junctions we looked at as a combination of 2 or more walls, and looked at junction parameters, which we will see much more detailed in later section. And finally, we looked at 2D and 3D classification of junctions and various alphabets of junctions and various types of 3D junctions, bar and corner and rotational junctions. This is also the fundamental language of casting design engineers. Okay. Remember, we are building a base for our later discussions. So all these look simple now, but you have to remember to be able to understand and come back to these logical points quickly. When I say thickness again, thickness change again, you should be able to come back to it very quickly. Okay.